Morning. My name is John Stephen Morgan.
I'm Aaron,
I'm Nicholas.
and this is our project on longevity genes by clustering. And so to start off, I'm going to explain the k-means clustering that I incorporated. And so we first started by reading the file, which is done in this function page right here. And we have it basically pull from these columns, each going into its associated list. And the way Python reads the file, it already ignores the title, so we didn't have to handle that. And so if we go back, this is where we read in the column names, and once we have the columns normalized, we will put it into tuples, which will be looking like something. If I type it out right here, it'll store it as 0.045, 0.0395, 0.935. And that's the way the tuple will look. And then we will go into setting the k amount by getting the user input. And so we then generate the initial centroid indices, which is done by a function generate initial centroid indices, which can be found right here, which we create an empty array and just have the k amount right here, and we just go through we iterate through the range and generate random numbers initially, and we then pull the tuple and put it to that centroid and return that array, and it's associated with this variable. And then this is where the function actually turns the index to the actual tuple, and that's just done right here. And then we go to old centroid, which just calculates the initial centroid, and then the new centroid will be turned into the old centroid after a few iterations. And so we just iterate through a specific amount of time, so 10 just for efficiency purposes, because we just want to demonstrate how it works. And so old centroid will equal new centroid, so we don't have that calculator right this second, so we just temporarily have it set. And so new centroid will call to recalculate centroid, and that'll be from functions.kmean cluster tuples old centroids. So once the k-mean cluster is calculated through a process listed right here, we will then return the associated centroid tuples, which basically stores what the specific points are associated to. So it'll store that cluster 1 or tuple 1, 2, and 3 are, say, stored in centroid 3 because it's the closest to that. And so it'll return and post it into recalculate centroids, which will then do the calculation through here, and it'll just basically take the averages of each of those and return the new centroids based on the data points associated with each centroid. And then it'll repeat that until the iteration amount is met, and so it'll basically find the closest exact value, and theoretically it should always generate the same value or at least really similar, and we just have it printed. So if we demonstrate it, just to make it bigger, I will do this and just click. And so if I just press it and then type in 10k, then it'll generate this array and it'll store the different k clusters. And that's basically how it works. And now we're going to go on to fuzzy means clustering, which will be presented by Nicholas.
Regarding fuzzy c-means clustering, first we give every data point a soft membership score for each cluster. It's basically just guessing how much that point belongs in each of the groups. We make sure the scores for each of them, the points add up to 1. Then using these scores, we compute each clusters center as a weighted average of all points, i.e., like points with higher membership will actually have more weight. And then next, we look at how far each point is from each of these centers, and we use these distances to update the membership scores. The closer scores, the closer points get higher membership in that cluster, and farther ones get lower. We repeat the cycle, recomputing centers and measuring distances, and updating memberships until the membership scores just barely change at all between the rounds. At that point, we actually found a stable set of clusters, which each of the points roughly belong to one or more of these groups. Regarding how we specifically used it to determine longevity to candidate genes, we're counting how many longevity genes are in each of these clusters, and we divided by the total number of genes in that cluster to get a percentage per group. If that percentage is high, like such as 60%, we treat the group as being particularly longevity rich. After which every cluster is flagged for its for how rich it is in longevity genes. After which we pull out any of the other genes that were on the original candidate list. We repeated this over the whole clustering and the selection process a few times at 40, 50, and 60 iterations, respectively. And we only kept the candidate genes that show up every time. This way, we would kind of zero in on a handful of other genes that most consistently grouped with the known longevity genes.
Ultimately, what we found with the k-means consensus is that the two longevity or proposed longevity genes here are MLH1 and TOM6. Now, with the k-means, we did use a 40, 50, and 60 iteration of the clustering, and these appear to be, say, the strongest, or have the strongest relationship with the known genes that we have from the very large data set. And then below, we actually see again some familiar names of the other two genes. There at the end, you see TOM6, so that one again showed up in the fuzzy consensus. And we also see the MLH1. Additionally, also we have the DIG1, DUR1 and 2, IN01, and the NUP100, SAP155. So all of those are showing up with a fuzzy consensus. Now, there could be definitely some more tests done in order to prove fuzzy consensus because, again, the number is so large, it's very possible some of these are not, they don't have such a strong relationship with the longevity genes as, let's say, the k-means consensus.